So for this example, let's take a look at a two-variable function f of xy equals x squared plus y squared. This is my go-to favorite function of the day. And we want to find the tangent plane when our point xy is equal to 1, 1. First, let's take a look graphically. Recall what this function looks like. Because my x-coordinate and my y-coordinates are both squared and my coefficients are positive, in this case 1, it means that we're looking at a paraboloid. So my horizontal traces are going to be these circles. And in both the x and the y plane, it's going to look like a parabola. So this is a sketch of what our graph looks like. And we're looking at finding a tangent plane when my x-coordinate and my y-coordinate are both equal to 1. So that's looking at something 1, 1, a point on the graph there. So let's find that point exactly. First, I'm going to evaluate the function at the point 1, 1, and it gives me 1 squared plus 1 squared, which is equal to 2. So it means that my point in three-dimensional space, I could label it here, is given by 1, 1, 2. My z-value is 2 in this case. I also, in order to find the equation for the tangent plane, I'm going to find the partial derivative with respect to x and evaluate that at the point 1, 1. So my partial derivative with respect to x is 2x. My y's disappear because they're constants. My partial with respect to y is going to be 2y. Again, my x term disappears because that's going to be constant. Important to note, when I am coming up with the equation of the tangent plane, just as in single variable calculus, I want these to represent slopes at this specific point. So it would be a mistake to leave my x here as a variable. I want to actually evaluate what is the slope right at this single point. So when I evaluate these, my partial at the point 1, 1 with respect to x is going to be equal to 2, and my partial derivative with respect to y evaluated at the point 1, 1 is also equal to 2. So that means that I'm ready to come up with the equation for this linearization. L of xy is equal to my z-coordinate, which in this case we said our z-coordinate was 2. We also wrote that as f of 1, 1, plus my slope in the x direction, which we found to be 2, times x minus the x-coordinate of the point, which is 1, plus my slope in the y direction, which is 2, multiplied by y minus my y-coordinate, which is 1. Let me label this so it makes a little more sense. So if I were to have the point 1, 1, 2, where are each of those pieces? The x-coordinate of the point is going here, the y-coordinate of the point is going here, and the z-coordinate of the point is here. You could also think of this as the z-component and subtract 2 from the z-component, just like we have here, only when I add it to this side, that's why it's positive. We also have our partial derivatives, f sub x evaluated at 1, 1, which I'll write in green, is the coefficient on my x term. And I also have my partial derivative with respect to y evaluated at 1, 1, which is the coefficient on my y term. So that's where all of these pieces are coming from. Maybe those arrows made it more confusing rather than less confusing. But written out this way, it still isn't the normal way that we would think of writing a plane. So let's do just a little bit of algebra to see why this is exactly what we would expect for an equation of a plane. I'm going to use the distributive property, everyone's old friend, and I'll write this as z is equal to 2 plus 2x minus 2 plus 2y minus 2. Hopefully I distributed that right. I have a positive 2 and a negative 2 and another negative 2, and I'm going to move all of these terms over to the same side like we typically do. So in this case, I would write this as negative 2x minus 2y plus z is equal to negative 2. If I wanted to, I might change the sign on this, just because typically we would not have a negative number on our right-hand side. So multiplying everything by negative 1, I end up with a function that looks like this. And this looks much more familiar to us as an equation of a plane. we can read off the coefficients on each of these to see that our normal vector for this plane, in this case, is given by 2, 2, -1. And when I take a look at what that looks like here in my graph, it measures up with something that I would expect. That if I were to sketch what this tangent plane sort of looks like, this paraboloid is arcing downwards, and I could see that my normal vector would be going out in the positive x direction, out in the positive y direction, and down a little bit in the z direction, because as the cup scoops, the normal vector would probably be pointing downwards a little bit. Another thing that we might want to check is, does our point actually satisfy this plane equation? If it didn't, it meant that I did some arithmetic wrong, which is possible. So let's go ahead and check and see that our point works. So I'm going to plug in my point 1, 1, 2 and see 2 times 1 plus 2 times 1 minus 2. Gosh, lots of 1s and 2s. Let's see what that equals. That's 2 plus 2 minus 2 is in fact equal to 2, meaning that when I plug the point into this plane equation, we got out what we would expect. So now I'm going to talk about some theory, and I know what you're thinking. I don't really like theory. You're probably a scientist. Maybe even if you are a mathematician, I'm not sure if you're into this type of theory. But I feel, as your instructor, that I would be remiss if I didn't at least mention the definition of differentiability for two variable functions. So the definition, as written on the board here in blue, assume that f of xy is defined in a disk containing AB. F of xy, we say, is differentiable, so this is our definition of differentiability, at the point AB, if our partial with respect to x and our partial with respect to y evaluated at the point AB exist. So those partial derivatives have to exist. Those are the things that we use to be able to come up with our linearization. And we also need the criteria that f of xy is locally linear at the point AB. And you're asking me, you're dying to know, well, what does it mean to be locally linear, Carolyn? This is a pretty useless definition if I introduce this term that you've never heard of before. So here it is, written in black below. We say that f of xy is locally linear at a point AB if the above criteria are met, meaning that these partials exist and that our function is defined on some disk, and that our linearization approximates our function to first order. Now, in sort of conceptual terms, what we're saying is we have some multivariable or two-variable function in three-dimensional space, and we want to know that when we approximate it with this plane, we want that planar approximation to be pretty good. That's essentially all that this is saying. It means that if we had a function that was really jiggity-jaggedy, that plane might not be as good of an approximation. So how good of an approximation, you ask? Well, this is our technical definition. Our function has to be equal to our linear function with this type of error, and where our epsilon of xy is some error function multiplied by this coefficient, and this is what makes it a first order approximation. Again, these are details that I'm not going to ask you to evaluate, but I think it is a good idea to have in mind mentally that as this error function approaches the point AB, so as my xy's get closer and closer to AB, this error function has to go to 0. So as I zoom in on my function using this linear approximation, I have these error terms, but as I get closer and closer, this error chunk has to get closer to 0. The thing that I do want to point out also is the idea that when we were talking about single variable functions, you don't need this whole linearization criteria. All you need is that the derivative exists. We said that if our derivative with respect to x, because it was just a single variable function, if that derivative exists, then we're done. That's all you need. The derivative, it's differentiable if the derivative exists, right? Whereas in a two-variable function, that's not enough. That just having the partial derivatives exist isn't quite good enough. We also need this locally linear property in order for our two-variable function to be differentiable.